So, thanks to the organizers for inviting me to the workshop and for sticking through it for a very long period of time and for giving me the opportunity to speak. What I'm going to do today is review some work which I did last year with a bunch of people and something that's ongoing. So, the title is about the problem I want to talk about is what I call the Dirichlet problem in AdS, but I'm going to talk a little bit beyond AdS asymptotics, and so that's the second part of the title. And this was work done last summer with my student Dan Bratton, Joan Kamps, who is going to be here, Logan Igam from Harvard, and something that we clarified in a paper with Don Murrell from earlier this year, and hopefully something that will appear later this month with Roberto Emparan and Veronica, myself. Okay. And the motivations for what this is about are somewhat the couple of motivations which I want to sort of address in some detail, and so we'll see how far I get in terms of actual details. There are quite a few details in the construction, but what I'm going to try to convince you is that the Dirichlet problem has a certain utility in being able to understand how gravitational systems work, and we will use this to understand. We'll use this mostly in a certain regime, the long wavelength regime, where we can make contact with fluid dynamics, and by embedding this problem in a slightly bigger arena, namely which is what this beyond is about, we'll try to derive a connection between the fluid gravity correspondence, which has been around for 4 or 5 years now, and what goes by the name of the black fold approach of trying to construct new black hole solutions in different asymptotic spacetimes. Okay. So let me begin with a sort of motivation for the talk, which I will explain in terms of the following. So we know that the fluid gravity correspondence relates dynamics of Einstein's equations and by these I mean Einstein's equations in asymptotically AdS spacetimes with the dynamics of fluids, especially dynamics of relativistic conformal fluids. In particular, if we take AdS spacetime and if we look at the Einstein's equations, which I will schematically denote as ER mu. So these equations, which are Einstein's equations for pure gravity in AdS with one leg along the radial direction and another leg along the boundary directions, these equations are nothing but the equations of motion of the conservation equations of a relativistic stress tensor, and in a particular long wavelength regime, these equations reduce, the stress tensor reduces to that of a fluid stress tensor. Okay. So this has been known for a few years. In fact, it predates the actual fluid gravity construction itself. We knew this almost a decade ago when people studied perturbations, linearized perturbations of AdS black holes, and showed that quasi-normal mode spectrum of AdS black holes exhibits properties that are fluid dynamics like. Now, there's an older story here which goes by the name of the membrane paradigm, which tries to, at the level I understand it, it tries to make an approximation of a black hole, and it also relates the physics of black holes to the physics of fluids. In particular, it tries to relate, it gives a, if you have a black hole and you excise the region inside some stretched horizon, then you can think of matter interacting with the black hole as matter interacting with some kind of fluid living on the stretched horizon. Now, there is a big difference between the fluid gravity approach and the membrane paradigm. In the fluid gravity approach, the fluids are the low energy limit of a field theory that we know, and this fluid lives on the boundary of AdS. Okay. On the other hand, in the membrane paradigm, there is no such, this membrane lives at the stretched horizon, and there is no natural sort of way to think about this in terms of some microscopic picture, right. So, this is the membrane paradigm as Damour and Thorne and Price thought about it, was supposed to be true for any black hole. It was some near horizon physics, and for them it was a simple way to think about black holes in terms of simpler objects endowed with properties that we could understand in terms of undergraduate mechanics without having to talk about general relativity. If you had the astrophysical black hole which was accreting matter, you didn't have to model all the nuances of general relativity to understand this. You could just think about how the matter in falling into a black hole interacts with this stretched horizon. Now, of course, as far as I understand this has never been derived in some proper framework, although I will describe in a moment what people think about this from a modern perspective.
What do you mean? You can write the answer in equations such that they look like that, as long as you allow for negative viscosity.
Yeah. So there are many subtleties. So okay. So the way I understand what Damour did, he takes Einstein's equations, he projects them on a null surface. It doesn't even have to be a horizon per se, and then he tries to do some kind of expansion and throws out some terms and identifies what he leaves as some kind of Navier-Stokes like equation. Okay. So and then the associated problems, because then if you try to look at that in more detail at the first derivative level, then you start seeing problems like this membrane that you have. If you try to give it properties, physical properties, it of course has shear and bulk viscosities. The bulk viscosity happens to be negative. Now, and as far as I know, that problem doesn't have a natural solution within the membrane paradigm as thought about in the old days directly. There are some resolutions, but I'm not convinced that they're good enough.
I would say that as long as you allow for the negative viscosity, then it's clear that you can derive these equations. I mean, the complications arise when you try to fix that. But the negative viscosity is something that you understand because of the teleological origin of the horizon, right? So
yeah, I'm not convinced that's all there is. And in fact, the more modern way of thinking about it, I think, will make it clear that there is a simpler way to think about this problem, and there is a description of this stretched horizon fluid which we can both study in itself, as some people have done, or you can embed it in this context, and in both cases you will find a fluid that doesn't have bulk viscosity. It's a much nicer fluid than what Damur would have derived. So that's one motivation sort of to ask, where is the membrane paradigm in AdS CFT? Where is, or what rather, what is a second motivation for me is a slightly more GR question, which relates to this point I just mentioned about black folds. Now, black folds were invented a few years ago by Robert Emparan, Niels Oberst, Rolf Harmack, and Basilis Niarchos as an attempt to try to understand general relativity in dimensions bigger than 5. And their logic was that once we go to, already when we go from 4 to 5 dimensions, the structure of general relativity, even vacuum general relativity, seems sufficiently rich. There are exact solutions like what Harvey and Roberto found, the black ring solution, which are not visible in 4-dimensional vacuum GR. And once you go to even 6 and higher dimensions, the structure of black holes, even the structure of known black holes, admits an interesting separation of scales. For example, if you just take rotating black holes in 6 and higher dimensions, they can rotate arbitrarily fast. There is no analog of a curve bound, and once the black holes start rotating arbitrarily fast, they pancake down onto the plane of rotation, and so instead of getting sort of reasonably spherical black holes, you start getting black holes that looks like turntables, which sort of are spinning. And once you encounter such situations, you realize that in higher dimensional gravity, there's a interesting hierarchical, there's an interesting regime where you have wide separation of scales. And when you encounter a hierarchy of scales, you can try to use some kind of matched asymptotic approximation to construct approximate black hole solutions, and this is what the black fold idea is about. So the idea is very simple. You imagine you start with some black object. So you take a black brane, which you know you can construct in higher dimensions. So let's take a black p brane in d dimensions. Now this would not be an asymptotically flat solution because it has translation invariant directions, but I can try to construct a black hole in d dimensions with flat d dimensional asymptotics by sort of wrapping this up on some compact region. Okay. So a good example is you take a black string, and I can sort of, if I wrap this up on a circle and set it spinning so that it's dynamically stable, I can try to construct an approximate black ring from a black string, and this is the idea behind this construction. And in this construction, there are sort of two sets of dynamics, two sets of dynamical modes these black branes have. And one way to think about it is, if I have a black p brane, then in d dimensions there is dynamics intrinsic to the world volume, and there is dynamics in the normal directions. And the intrinsic dynamics along the world volume at long wavelengths is fluid dynamics. The extrinsic dynamic is a bit more complicated, and I am not going to talk about it. It's been understood quite well recently in a paper by Roberto and John Camps. And you can think about this as the dynamics of elastic solids. So, in some sense, black branes in higher dimensions behave like fluids when you perturb them along their world volume, and then if you try to bend them or wrap them, they behave like elastic solids. Okay. Now, the question is, this sounds awfully similar to what I was saying here, and in fact, the derivation is very reminiscent of the kind of construction that was done in the fluid gravity context. And our natural question is, what is the connection between the black fold approach and the fluid gravity approach?
So, a small change in the horizon, you will include that in the intrinsic dynamics or the extrinsic dynamics?
So if by small change you mean, if you think of slightly heating up the horizon locally, I would think of it in terms of intrinsic dynamics, and that's how we think about it in this context, right? We have a horizon in the bulk, which was equilibrium, which had constant temperature at equilibrium, and then we sort of locally fluctuated it, and that would sort of be encoded in fluid dynamics, and that part is already included in this intrinsic.
So, is it accurate to say the extrinsic dynamics are sort of ones which are separated by a gap in some ways, or?
No. So, one way to think about it is that there's one set of, well, this problem of a black brane in d dimensions has two sets of Goldstone modes. One set corresponds to the fluid dynamical Goldstone mode that I'll describe in this context, but the other corresponds to the Goldstone modes associated with broken translation invariance, just the presence of a brane which breaks translation invariance in the transverse direction. So, there is some analog of some kind of dBi action, but now it's sort of, it's not just dBi, it's souped up in some sense, and that is this dynamics. So, if you had an extremal brane, I would think of the elastic solid behavior as analog as being captured by the dBi dynamics coming from that broken translational symmetry. Now, of course, these are not totally decoupled, because in the real problem they will be fully coupled. At leading order they do decouple. So, if you sort of talk about first order fluid dynamics and first order elastic solid dynamics, at that order things decouple, but they stay coupled beyond that. But yeah, I will not say very much about this for today. I am going to sort of concentrate more on the intrinsic dynamics and show how that can be related to this framework. Any other questions? Okay, so the punchline of the talk, or what I would like to hopefully show, is the following: that there is a natural sort of inclusion that one can construct, and one can show that you can sort of derive fluid gravity out of this generalized construction involving black folds. And I mean, here I am doing fluid gravity in a sort of narrow sense as fluid dynamics in asymptotically AdS spacetimes. I think at some basic level there is not so much difference between these two pictures, and these naturally include the membrane currents. And this is the inclusion I would like to explain to you in some detail in the rest of the talk.
Are you going to explain this hierarchy of scales? Because in what you've said so far, I don't see where this hierarchy is.
I'll explain it in a slightly different language in time to come.
Fluid gravity you said was AdS, right?
Sorry?
So fluid gravity was an AdS.
The fluid gravity was in AdS.
The membrane paradigm was originally considered not in AdS.
So we'll get there. So we'll get there. I will show you one model which includes features of all three, and that's the content of the
realization of the membrane paradigm.
Very good. Thank you. Yes. Yeah. Shall I say the correct realization of the membrane paradigm?
It's being recorded.
Sorry?
It's being recorded.
Don't remind him.
Okay. So So let me first talk about this half, which is a bit easier to understand, how to realize the membrane paradigm from the fluid gravity context, and then do the second inclusion later. So here's what we'd like to do. So let's go back and think about fluid gravity in AdS, asymptotically AdS spacetimes. And let me draw one picture, which I'll probably never use, but let me draw it. So in the fluid gravity context, what was constructed was given boundary dynamics. So boundary data was a metric at the boundary of AdS, really a metric in a particular conformal class, but I'll just say a boundary metric. And we introduce, and we have a hierarchy in this separation of scales. We have a long wavelength regime, about some equilibrium solution at some finite temperature. Now we know that in AdS CFT, if you have thermal equilibrium at some finite temperature, the dual geometry is given by some kind of black hole, and I'm not really specifying what kind of system I have. It could just be the Schwarzschild radius black hole if I'm talking about neutral fluids. But if I'm interested in more general fluids with carrying various charges, what have you, this could be some charged black hole carrying appropriate charges and so on. So take the system, and at equilibrium this would just be an eternal black hole. Now if I go to long wavelength fluctuations about thermal equilibrium, what the fluid gravity construction showed you is that you could construct an approximate solution in the bulk by piecewise patching together these equilibrium black hole solutions along these ingoing null tubes. Okay, so I won't go through the construction in any detail. We won't need very much of the details of the construction. So the essential point, remember, is the following: in fluid dynamics is a theory that's an IR effective field theory that's valid near equilibrium. So if I have global equilibrium, I have global notions of thermodynamic quantities, and I can construct some black hole solution that dually in a gravitational sense realizes the fluid dynamical thermodynamics as a consequence of black hole thermodynamics. However, if I am sort of near equilibrium, I can look at a local patch, and in a local patch the fluid looks like it's again in global equilibrium, some domain set of some size set by the characteristic scale. So if I have just a neutral fluid, the characteristic scale is set by the inverse temperature, the local temperature inverse, and in that domain I have a fluid of some which is isomorphic to the global equilibrium fluid, and that domain in the boundary can be extended out into the bulk to construct in this tube a bulk solution that looks no different from the black hole solution that we would naturally construct. And putting these tubes together, you would construct an approximate black hole solution that we gave a prescription for algorithmically how to construct. So given this boundary metric, you have a boundary stress tensor which you get by the usual Brown-York construction. So this is some extrinsic curvature of the metric plus counter term pieces which you want to write out, and this takes the form of a fluid dynamical stress tensor plus higher order corrections, we can, so here's the hierarchy. The hierarchy is that sigma mu nu is so I'm going to call this guy P mu nu. Sigma mu nu is a shear tensor constructed out of the velocity field by taking the spatially projected transverse traceless gradient of the velocity field. Okay, so the logic is that we do this as in effective field theory. Gradients are suppressed relative to the 0th order piece, and the measure of gradients is in terms of these parameters which are assumed to be small. Okay. Now we have these solutions, and we can obtain
T there
is a local temperature
is a local temperature.
at any point, and the gradients of local temperature and the gradients of local velocity in units of local temperature are said to be small. So that's the construction, and once you have the bulk solution, we can read off and you can fix these transport coefficients, and that's what was done on the boundary. Okay. Now we want to do something else. I want to make contact with the membrane paradigm, and I want to therefore ask the following question. Suppose I didn't want to sort of specify the metric at the boundary of AdS. Okay. I instead wanted to fix my metric somewhere on some random hypersurface in the middle of AdS. So I'll pick some time-like hypersurface in AdS, and let me draw a slightly different picture to illustrate this. So here's my horizon, and here was the boundary of AdS, and the sort of membrane paradigm picture seems to suggest that I should be sort of trying to define dynamics on some stretched horizon near the membrane, near the horizon, and so forth. So let me be a bit more general for the moment and ask the following question. I'll pick a random time-like surface in the middle of AdS. Okay. So let me call this surface sigma. So this is at some location r equals r d for Dirichlet in the middle of AdS, and we can talk about how we fix this surface. If you have some additional fields in your problem, you can talk about this surface in some in terms of some relational sense. You can say if you have some scalar field, you can fix the surface by declaring it's a surface at some fixed value of the scalar field. Okay. So you don't have to talk about it in terms of coordinates, but let me imagine that I just pick some radial coordinate in some gauge and say this is a surface at r equals r. I want to do the following. Given the surface, I want to fix my metric on the surface, and I want to let the black hole adjust to this new restriction. Okay. So the black hole will adjust, and I want to solve Einstein's equations in this interior region, what naturally we would call the IR region, and read off having solved the black solution with this metric with this hypersurface metric fixed on the surface and a natural notion of regularity at the horizon. I want to ask what stress tensor can I induce on this surface. So let me call those metric and stress tensor g hat and t hat, because they are going to be different from the metric and stress tensor that I am going to define on the boundary of AdS. So this is my definition of the Dirichlet problem. The Dirichlet problem is simply defined by saying I pick some fiducial surface, I fix the metric on it, and ask what is the bulk's response, what kind of stress tensor do I get. I actually am also interested in the following. I want to know what do I need to do on the boundary of AdS, okay, where I have my metric G mu nu and an associated stress tensor T mu nu, such that I can obtain my Dirichlet boundary condition. Okay. This is going to be important because that will allow me to make contact a bit more precisely with the membrane paradigm when I come to it later. Okay. So that's the data. The data is simply this. I want a map. I want to first find okay. And I want a relation between this data, which is the set G hat T hat, and the boundary data, which is G mu nu T mu nu.
These questions translate into natural questions from the perspective of the boundary field theory?
Natural, I guess, depends on your perspective. I will say there are certainly things you can consider on the boundary. So I'll give you a simple example in a moment, and you'll see what's funny about them. So this is a particularly nasty problem because things are nonlinear here. Gravity is nonlinear, so it's not clear how to do this map in general. So I will show you that there is a solution to this map in this long wavelength regime where we can talk about it, and that's because of some simplifications that happen when you only consider fluctuations that are sufficiently slowly varying in these directions but arbitrary in the radial direction, which is the context of the fluid gravity story. So just to give ourselves some intuition, so consider a simpler problem. So consider a scalar field in the bulk, okay, and let's say we want to do the same thing. Now usually you would say you fix the value of the scalar at infinity, and then you read off, given some interior boundary condition, you read off the wave for the scalar. Now instead you want to say, no, I don't want to fix the value of the scalar at infinity, I want to fix the value of the scalar at some intermediate position in AdS. Okay. It's clear what you need to do. You need to correlate the scalar wave and its source at infinity precisely so that you hit a node and the scalar takes on the value you want it to take on at this surface. So since for this linear problem it's clear that the scalar Dirichlet problem requires fine tuning sources and waves, and it's also clear that this relation between source and wave is not local on the boundary. So for linear problems, is some non-local multi-phase deformation on the boundary of AdS. So we are certainly free to consider such a boundary condition. We might not, as field theories, want to think of it as natural, but they seem completely natural from the point of view of the bulk construction. But I should say that this is not specific to picking the Dirichlet boundary condition. Any choice of boundary conditions on this surface requires some correlation between sources and waves, And that correlation will not necessarily be local unless you do some real fine tuning.
Isn't it just regularity? It's the same thing with a post, right? Because
Yeah. So
isn't it just regularity at the? It's the same thing we would have imposed anyways, right? I mean, the only thing we're tuning is the free parameters such that the field is whatever you want it to be at that slice.
actually, I think it's independent of the regularity issue.
But that's what you're assuming, right? Because if phi and its derivative take a given value at that slice,
Yes.
then they're all going to be regular.
Yeah, I agree. But we'll see that something simple happens in this in the gravitational problem in the long wavelength regime. But the general picture I would like to the general lesson I would like you to take away is that this is generically true, that any choice of boundary conditions on the surface is necessarily going to involve you correlating sources and waves on the boundary of AdS, and that might not be a nice boundary condition as far as field theory is concerned. You don't look very happy.
I don't understand. What's the data? I mean, you need to give me two pieces of data to solve the problem.
Yeah, so for the
There's
scalar,
phi and what else?
so for the scalar, I cheat a little bit. I don't give you regularity in the interior. Okay, because if I give you a regular source, if I give you a Lorentzian AdS, and if I have Klein-Gordon scalar, there's no solution that's, the only solution is zero wave and zero. So if I relax that, but for the gravitational problem, there's a non-trivial solution to this, to having fixed metric here and regularity here, which is what I really want to describe. Yeah. So all I want you to take away is that this is a problem that you can just do in the back of an envelope. Just use standard solution to the scalar field equation of motion, and you will conclude this without any work. Okay, so let's ask what happens in the context of gravity.
Why non-local? I guess that's what I'm.
Yeah. So why non-local? The easy way to so think of solving this in Poincare AdS. What would you do? And let's do this in a fashion that actually is going to. I mean, the technical answer is you have to invert Bessel functions, because scalar wave equation solutions are Bessel functions, and you want to sort of have some relation between the sources and waves, which involve these Bessel functions. But a better way to say it is just take the
Bessel functions just depend, and the Bessel functions in R.
Yeah, but now yeah, so let me say this slightly differently, which will make clear non-locality more manifestly. Just solve the problem in a gradient expansion. Right. So pick. So if I have phi, then phi is phi 0, phi at the boundary, r to the minus gets d minus delta plus j phi r to the delta minus d. Yeah, and this is at zero momentum. This is the solution. Now I just want to say phi at rd is phi d, and we can solve for phi d in terms of this, and just rearrange this to find the source. Let's call this phi 0 hat. And then there's a wave which is j phi hat. So we can solve for the source and wave, but now we can do corrections in small momentum, and the corrections are non-analytic in momentum, because they're k to the power nu that come when you do the mode expansions. Yeah. So basically delta enters everywhere, and corrections are set by k to the power delta, and that's the source of non-analyticity in the scalar problem.
Isn't the scale of non-locality essentially like if you draw a triangle?
Very good.
If you take a point on that and then
draw shine a shadow,
then,
it's said by the.
Could be the scale of non-locality,
right.
Presumably because
Yes.
you would have to correlate things on that scale for it to precisely have a value.
I mean, that actually also visible in some constructions that people have done to look at local bulk operators constructed out of boundary fields. Yeah. So
Did, for example.
we did. This was Kabat and
Similar with your
yeah, we had causal constructions, but we had surfaces. But Kabat, I think it goes back to Banks and Company many years ago. But Kabat, Lifshitz, and Lowe, in a series of very nice papers, tried constructing what they would call a local bulk field out of a boundary operator. So that's like constructing a bulk to boundary propagator, but not with boundary sources, but with boundary wells. Right? You want to take a boundary operator and map it to a bulk field. And that indeed, as Rajesh said, yeah, I want to talk about phi at R and X. That guy, the natural way to get it is to smear the operator over an entire light region, which is sort of space-like separated from phi, and in global AdS it's actually sort of on both directions. But so that's the scale of non-locality that you should expect in this problem, and that's what you explicitly see from a construction. Okay, so what happens in the gravitational problem? So it sounds like we are in a bit of a mess, because not only do we have to do some kind of mapping like this, but we have to do it in a nonlinear regime, and I have no idea how to do this in a nonlinear regime. However, things are a lot simpler in this fluid gravity context, because the surface of the kind I drew there is a surface that looks like, if there isn't yet another color, there is another color. So I want to draw a time-like surface in the bulk, and that time-like surface I could draw as some surface that sort of cuts through. And I just emphasize to you that the geometry in the fluid gravity context doesn't really change in these domains. It's the same as a well-known black hole solution in this domain. It's just that nearby domains have different temperatures and they look like different black holes. They're just patched together. So because of this simplification, it should be no effort to sort of start here and then push myself forward along this ingoing null geodesics, along these tubes, and instead of starting at the boundary. And this is what we did in our paper last summer. So the obvious thing to do is just put your data here and try to solve Einstein's equations with this boundary condition at the surface, and ask what solutions do you have with a regular horizon in the interior. A much simpler way to solve the problem is the following: is to look at the fluid gravity solutions as a function of boundary metric. Okay. So these are fluids that live on some curved space-time on the boundary of AdS, and these are known. These have been constructed explicitly for any sufficiently slowly varying g mu nu. I should say that when I'm talking about fluids, the constraint that I have this long wavelength should not only be true at the level of the fluid dynamical variables, but also for the metric. So in particular, this metric is something that's sufficiently close to flat. The gradients in this metric, the curvatures, are also sufficiently slowly varying. So take this family of solutions and then slice them appropriately so that at our chosen surface r equals we induce the correct metric. That is peak g mu nu such that induced metric at is exactly the metric you want. Okay, so this is algebraically equivalent to actually resolving Einstein's equations, but the point is that we have a moduli space of solutions parameterized by the boundary metric. So you might as well choose your boundary metric to achieve what boundary condition you want at some intermediate surface instead of having to resolve the problem. Okay, so this part is a bit of algebra, but you can do this, and what you find is the following. It should be no surprise that the stress tensor that you construct, so you find the solution, you've already solved the problem, and then you can induce a stress tensor on the surface, and this stress tensor takes the form of a fluid stress tensor where I have written everything in terms of the variables that are intrinsic to the hypersurface having and not to the boundary. Okay, I'll come back to the boundary in a minute. Yes?
So you use the same formula to calculate this stress tensor, is it? I mean, like.
Yes, thank you. So there's an important story here, which is that this piece of the stress tensor that comes from the Gibbons-Hawking term, which is all that I need to impose Dirichlet boundary conditions, is automatically conserved by itself. Right? So this is the Brown-York stress tensor, and you can check that this is obviously conserved by the Gauss-Karadzy equations. The counter terms we write down on the boundary of AdS because this guy diverges. Right? So we write down counter terms to extract the finite part of this. Now you're right that I'm at a finite cutoff, so I don't really need counter terms, because whatever I get from this Brown-York stress tensor is manifestly finite. However, if I demand that I have a continuous limit as I take the surface out to the boundary, the natural thing seems to be to use the same set of counter terms that I would use on the boundary of AdS. So the definition we are using is take the definition of the stress tensor that you have on the boundary of AdS with all its associated set of counter terms and evaluate that guy on the surface, having had the solution.
So there's no independent way of thinking about something living on the Dirichlet surface and computing counter terms for that. I mean,
well,
you have to actually fall back to the.
The thing is, I claim that the counter terms are now up to you. See, the way usually things work is that if I give you, say, gravity in a box with this Dirichlet problem, all you need to prescribe for me is a boundary term that makes the variational principle well behaved. Then there's an issue whether the on-shell action or things you compute out of that action principle are finite or not. If they're not finite, then we can add local counter terms to make them finite. That's some regularization procedure. But if you're at finite cutoff, there is no need for regularization. I'm just saying that we are going to adopt a prescription which agrees with the boundary prescription, but a priori is not required. So we could have just evaluated this and you'd have gotten slightly different answers. But I think this is more natural. And so to answer your question, we did use the same definition as you would use on the boundary of AdS.
Hamiltonian constraint in terms of the fluid variables?
The Hamiltonian constraint. Okay. So this is an interesting, I don't think of the Hamiltonian constraint as part of fluid dynamics. In particular, one of the things we did when we solved Einstein's equations is we actually used the Hamiltonian constraint would have been, roughly speaking, the RR component of Einstein's equations. We used that as a dynamical equation. Now, let's see. Some people, especially the modern version of the membrane paradigm, they like to use that Hamiltonian constraint as a constraint on fluid dynamics itself, and they write a relation which is something like rho squared equals something, which I don't fully understand. But for my purposes, I think the Hamiltonian constraint is part of the dynamical equations. I will only worry about this set of equations, which are the conservation equations. So there are many things I can say about this. So I won't go through the derivation. In fact, I'm not even sure how much I'm going to say.
What is eta hat?
Yeah, so I'm coming exactly to that point. So first thing is that this fluid is not conformal anymore, right? Because this fluid is at has some intrinsic scale associated with the location of sigma. So this is not a conformal fluid. So in particular, rho hat plus p hat over d minus 1 is not 0. Okay, there are expressions which you can write down. They're not very illuminating. And to answer Spenta's question, there are two quantities I should write down here. This is no longer a conformal fluid, so there could be a bulk viscosity, and there is some shear viscosity. And you do the computation, and you find that eta hat is the same as eta on the boundary, and zeta hat stays 0. Okay. So this is just a result of a computation. This part I think was presaged in a paper by Hong Liu and Nabil Iqbal, where they tried looking at how the shear viscosity runs in AdS spacetimes, and they showed that in using Kubo formula it doesn't run in the linearized theory. This is just a nonlinear version of that statement, that even in nonlinear gravity things don't, this eta hat doesn't run. Now that we have this piece of data, we can finish the second part. I can give you a map between g hat and g, and we can solve for g in terms of g hat and u hat. There's some scalar function here plus correction terms, but it's more useful to write this answer in terms of the fluid dynamical variables itself of the boundary. And what you get is that the boundary metric is a hypersurface metric plus correction terms that are proportional to tensor structures built out of the fluid variables. And I think this formula explains everything much more cleanly than what I was saying up there. So let me say what this says. So this is the map I was looking for. This would be the map between g mu nu, t mu nu, and g hat, t hat. But I've just rewritten, having already solved for u hats, the hypersurface velocities in terms of boundary velocities, so that I have now the boundary metric is a piece which involves some fixed background metric, which is the metric I've picked for my Dirichlet problem, plus correction terms which are built out of fluid dynamical variables. Now think about a fluid propagating on this background. Our boundary fluid is a very nice fluid. It's a conformal fluid. We understand it. It's the fluid of n equals 4 super Young Mills. However, now it doesn't live on a fixed background. The fluid lives on a background which is given in terms of some metric that I have chosen, but and terms that depend on fluid dynamical variables themselves. Okay. So this is as if there's a fluid that's moving. It's being forced by a background metric, but it carries with it a self-gravitational cloud. It has a gravitational cloud depending on what its local temperatures and velocities are. And there's a precedent for this. We don't think about this in fluid dynamics, but of course we think about this in electrodynamics. If you have a charged particle moving through polarizable medium, you can either think about the electric and magnetic fields produced in the medium as the charged particle propagates, or you can subsume the and talk about screening, or you can subsume the effects of the polarizability and talk about a dressed charge that moves through an inert medium. We have exactly the same kind of physics here. We have a fluid that moves through a dynamical medium. Medium is dynamical not because the metric is dynamical, but because the metric depends on dynamical variables. The conservation equation here, d mu t mu nu equals 0, t mu nu being this guy, has contributions both from the derivatives coming from those explicit terms in the stress tensor which are proportional to velocities and temperatures, and from the background. there is no Einstein equation, but the background is not determined until I have solved fluid dynamical equations of motion. But this problem is equivalent to the conservation of the hypersurface stress tensor with respect to the hypersurface metric. And while this description is like a fluid moving on a quote unquote dynamical background, this description is what we called a dressed fluid, but moving on an inert background.
This now looks local. Is that right?
This is local modular subtlety. It's low. So the fluid in this long wavelength regime, this is like a double trace deformation, right, because this is some fixed metric. This is like the stress tensor. There's one piece here which makes it somewhat tricky. There's some transcendental function of some variable here multiplying the shear, which we can't invert. So it's not totally clear to us whether. So I would say it's mostly local, apart from inverting this transcendental function.
Are you working in a regime where your wavelengths are much longer than the projection of that triangle on the boundary, so that
Yeah,
you smear over the
I
locality?
think so. Yeah, yeah. I think that's a good way to say it. But as far as fluid dynamics is concerned, this is certainly something we can do. We can make a fluid carry with it some self-gravitating cloud, and you would get this. But the whole reason to bring this up is that now I can explain to you what the membrane paradigm is in this context, at least what, as Harvey said, the A version of the membrane paradigm in AdS CFT. And all I need to do is move my surface all the way close to the horizon. And what happens in this limit, which is, since I have 5 minutes, so is that the fluid on sigma becomes incompressible and consequently non-relativistic. And much of this you can understand from the kinematics. The point is, I want to talk about a fluid on a time-like hypersurface. I'm pushing my surface closer and closer to the horizon. I have to account for an infinite redshift. It freezes all energy fluctuations. That makes the fluid incompressible. The boundary metric in this limit degenerates. Instead of having a nice Lorentzian manifold, I end up with a manifold with a Newton-Cartan structure. And the Newton-Cartan structure is very simple to understand. You don't have a metric, you have a inverse spatial metric and a time function, okay, because you have it's intrinsically non-relativistic system. It breaks the space-time isotropy, and this is the story. So the claim is, if you want to describe membrane paradigm in AdS CFT, take n equals to Yang-Mills and stick it on a background with a Newton-Cartan structure, and this derives for you a version of the membrane paradigm. And this is the version of membrane paradigm that has been derived by Andy Strominger and company in the context of the local Grindler dynamics, which is all that we see in the near horizon limit. And this answers Diego's question. Because the fluid goes incompressible, you don't see bulk viscosity. The mode that would couple to bulk viscosity is the expansion mode, and that's frozen in this limit. So So you don't get a compressible non-relativistic fluid as Damour would have wanted it, but you instead get this incompressible fluid.
This statement I heard earlier that the shear viscosity is negative in the usual.
No, bulk viscosity is negative.
No, the shear viscosity is negative. In the original.
No. Shear viscosity always was 1 over 4, was 4 entropy density over 4 pi.
Opposite sign,
Yes.
the way it was originally written with the
That
fluid
was
of
bulk
Janus.
viscosity, which was
Yeah, it's
shear was always.
shear was always, I think, well defined. And since David is going to shut me up in 2 minutes, let me give you a 2-minute summary of the black folds, which is actually, I think, cute, and it's not so much of a stretch of imagination once you've seen all this structure to see where to go. You want to sort of generalize this story to asymptotically flat spacetimes or what have you, and there's a very, very natural context where we can do this, which is the context which I guess there are a few people in this room who predate AdS CFT, is just take the non-extremal D3 brane solution. The kind of things that people played around in the early 90s, this exists. So this is an asymptotically flat region. It has an AdS throat, and it has a horizon somewhere way down. I'm talking about the non-extremal case, so it has a finite AdS throat. Now play the Dirichlet problem here. Put some, you can talk about this 3 colors. So this is the near horizon, this is the throat, and this is asymptotic region. Now this geometry has multiple scales, right, because it's pre-decoupling. So there's a thermal scale, there is a scale set by the D3 brane charge, or rather the scale set by the throat, where the throat opens up, and there's the asymptotic regime. Now if we had been working here and doing the Dirichlet problem, we precisely have recovered the story of the black folds, which I haven't had any more time to describe to you in any detail, but you have to believe me that the construction that I'm describing at the flat space infinity is precisely the black fold construction that various people describe. If you do the Dirichlet problem down in the throat, we should get the fluid gravity regime, because this is if you sort of have a near extremal brane and you decouple the throat, this is the AdS boundary, and you should see the conformal fluid living on this boundary. And I just showed you that if you work here, you see the membrane paradigm fluid of the local Rindler geometry. So this is a context where you can sort of embed in a single geometry the 3 different regimes, and you can interpolate between these 3 regimes by tuning the parameters and seeing how the fluid description changes as you go from the asymptotically flat region to the throat and then down to the membrane. And it turns out that for much of the physics, the region beyond the throat is subdominant, that the conformal fluid controls a lot of the asymptotically flat dynamics of this in the near extremal region. If your brane, however, is very far from extremality, then your horizon enters the AdS throat and sort of sits somewhere here. Then you expect to see interesting physics like Gregory-Laflamme instability, which you can also see from the fluid dynamics picture. But explaining all that will take me much more than 2 minutes. So in light of time, I'll stop there with that picture.
Questions? That is going back to the Dirichlet problem in AdS.
Yeah.
I mean, if you, for instance, didn't consider this specific counter term, I mean, you would have probably this bulk viscosity which is non-zero, right?
You're probably right. Let me think about it. I'm not 100% sure, but I think you're right.
But I was wondering if then you take this surface to the horizon. I mean, if you take this, do you still get incompressible fluid, or?
Yeah, I mean,
is that
I think this is necessary. Yeah. So the way I didn't describe any of the detail, but the way this limit is taken is you hold the local temperature as seen by the observers living on this surface fixed, and that temperature is that local temperature is diverging. And since that local temperature is diverging, local energy densities are diverging at some rate, and you can see this. There's a separate computation you can do, which is independent of any of the details of counter terms and so on, which is just to compute the quasi-normal mode spectrum, which is what I did in one of the other papers, with the Dirichlet boundary condition. And you will see the speed of sound diverges as you go near the horizon, and that's sufficient to argue for incompressibility.
I mean, would it be fair to say that this extrinsic dynamics of the black fold that disappears when you go down to the throat?
Yes. So I think that extrinsic dynamics, those modes that get frozen in the throat. Whereas if you sort of go away from the throat, you should be able to see them. In some sense, it's like having the branes, the D3 branes fluctuate in the 5 sphere directions, but that dynamics is completely frozen in the decoupling limit.
some speaker? Thanks.